All right, here we go again. So thank you for the introduction. Welcome everyone to today's lecture in today's online training week. This has been a lecture that I do per request, basically. So I was asked by the doctoral candidates to talk about not just sensor data reduction, as it was maybe announced in the program, but specifically about using the principal component analysis for dimensional reduction, of course, in the context of sensor data. So I have some material prepared, but since this was given by request, again, today, even more than usual, anytime you want to interrupt me, you have a specific question or something specific you have in mind, go ahead and ask me. I'm here to serve you, basically. And also for this purpose, I actually decided not to really prepare, let's say, a full-blown PowerPoint presentation to which I just guide you. I have very few introductory slides in the beginning as a motivation, but then actually I want to do more like handwriting, going a little bit through the underlying concepts, just to sort of reiterate and maybe get a bit of also geometrical grasp of what's actually happening inside the SVD and the projectors and the PCA. I hope it's not too boring for you. I think you guys have different levels in terms of how familiar you are with concepts of linear algebra and statistics. So I'm hoping to help everyone. But if you feel it's sort of too boring, you already know all this, then please stop me. I mean, there's no need that we need to go through everything again. But maybe it's helpful, maybe not. I do have some Python examples. I do want to do some live programming and shoot myself in the foot by trying to do that because I'm not that versatile in Python myself, but this is the only way we learn, tossing ourselves in the cold water and really trying hard. So let's see how that's going to go. I do have some examples prepared that are a bit more involved because we won't have time to program everything. But let's see, if you want, you can always follow along for the Python programming. I'll be slow enough so you can just follow along as I'm typing and do your own sort of experiments and tests alongside the stuff we do. At least that's the plan for today. So let's see. I have 2 hours in total, including a half-an-hour break. So let's see when we do that. All right, so I've said everything that's on the slide. So let me go to the next one. I do want to start with a bit of motivation. Why do we talk actually about dimensionality reduction, particularly in the context of the USES2 Marie Curie project, where we talk a lot about monitoring. And I think monitoring is an excellent example why data reduction is so important, which is one reason why we are here as a partner, because this is really what we do, data reduction. Why? Because the amount of data we're dealing with in monitoring applications is potentially really huge. Just think about it. What does the dimensionality of sensor data depend on? Well, first of all, it depends on the number of sensors, obviously, but particularly in monitoring applications, yeah, of course, it depends a lot. And sometimes you use a single sensor, but more often than not, it can be dozens. It could even be hundreds or more. And in fact, a lot of the work that we do in the project aims at making the sensor more energy efficient, more data efficient, such that they can be embedded in small sort of cheap devices in order to scale up, in order to have more sensors deployed, because the better we have them deployed, the more uniform we will be able to gather data. So actually scaling up the number of sensors is something that we aim for. But of course, that also scales up the data amount if you don't do it right. And the other thing it depends on is the number of samples and time. So how many samples does each sensor collect, which itself depends on the sampling rate at which the sensor runs times the total sampling duration. Yeah, so you can have a sensor that samples at a very low rate. So it takes readings every couple of minutes, maybe if it monitors a temperature or something like that. But then it runs the whole time for months or years. Or you can have sensors with very high sampling rates, like collecting ultrasonic data. Yeah, think of Coda wave data, but they won't be running the whole time. They will run in bursts, and then they will there will breaks between. But what matters is the total sampling duration. So again, in terms of the sampling rate, as I just said, it depends very much on the application, and we cannot say in general. It could be millihertz if we sample every minute or hour or so, like at temperatures that are changing slowly. It could be kilohertz, it could be megahertz if we're talking seismics or even ultrasonics. Yeah. So depending on the material, in concrete, we would be maybe still in the kilohertz. But if we're talking composites or maybe even steel, then we're actually talking megahertz. And yeah, the sampling duration, as I just said, again, it depends a lot, of course. But very often we sample in bursts. So one burst could be then milliseconds, microseconds, if you're talking megahertz or maybe seconds. But then there's going to be repetition of those bursts, and they could go on for hours, for days, for months, sometimes years. So if you multiply everything together, what you find is your mileage may vary a lot. But very quickly, in many monitoring applications, we generate gigabytes, we generate terabytes, and sometimes even more than that. And that could potentially be a problem for multiple reasons. You need to sample all this data. You need to, which costs some energy that you may not have available, especially if you're talking about autonomous sensors. You need to transmit the data somehow. And yeah, maybe you're lucky and you have a fiber connection to your sensor, but not always. We're talking about wireless sensors more and more. We're talking about sensing in remote locations. Yeah, so even if you have wireless sensor network that's well connected, maybe it's attached to some bridge that's in the middle of nowhere where there's no nice 5G uplink, just a very low bandwidth internet connection, or maybe some, I don't know, remote tunnel or whatever. So transmitting the data is often the biggest bottleneck, in fact, for remote sensing and autonomous sensor networks. And then even if you have the data somewhere, you need to store it. Storing data can be expensive. You need to maintain it, and you need to be able to find anything in the data. So if you're looking for specific things and you generated yourself terabytes and exabytes, you generated yourself a big data problem, then requires specific methods to be able to work with the data you generated. And that could be a problem. And it's not necessary. And that's the other claim I keep making. Almost every presentation you see from me claims this is not necessary. Why? Because sensor data is often highly redundant. So I brought some examples here that are, of course, sort of a little bit more optimistic examples, but they're real data. So the above is a seismic data scan that I found somewhere on the internet. The lower one is an ultrasonic scan that we made ourselves. And what you can see in both cases are adjacent traces, so taken at adjacent points in space. The other dimension being the actual time, so the fast time along which the recording has been made. And what you can already see by visual comparison is they look quite similar on the one hand. So there is spatial correlation. Adjacent scans don't vary too much. And there's physical reasons for this. If you make a dense ultrasonic scan, what we're actually sampling is the wavefront of an acoustic signal. And the wavefront, for physical reasons, cannot change really abruptly. Yeah, there's continuity conditions, especially if you are on a continuous surface. So there must be an amount of correlation. Of course, it depends on what kind of wave phenomenon and how fine are you sampling, but the gist of it is there must be. So it's not surprising adjacent channels are similar. They're not the same. It's not like I can just leave away half and not feel the difference, but they're similar. There's correlation in a statistical sense, which we can exploit. And in fact, even in time, you can see they have a very similar structure, and there's lots of zeros, and in between there is some pulses that look kind of similar. So there seems to be a lot of redundancy. And the big question that we keep asking the whole time is, how can we make use of that? How can we exploit the fact that we know that all this big data has redundancies in order not to retain each individual sample, because not each individual sample is going to carry information, but only the part that is relevant. This has to do with the work we do in compressed sensing, but this has also to do with the content of today's lecture, the PCA. And I'll draw the connections between compressed sensing and PCA later today. For now, just to emphasize that again, so there may be redundancy in space. Adjacent scans are similar because we're doing a dense sampling of relatively smooth wavefronts. There may be sampling in so-called fast time. So when I say fast time, I mean the actual time during which the, let's say, ultrasonic wave propagation phenomenon takes place, which is on the scale of microseconds. Yeah. So lots of reasons. One is we have resonant phenomena, especially in ultrasound. Ultrasound itself is a resonant phenomenon, meaning that the physical devices that generate and receive ultrasound are band limited by themselves due to the nature, which is why what we see often looks like modulated short pulses, but there is a modulation, meaning that the entire spectrum is not occupied, but there is a certain part around a resonant frequency that's occupied and the rest of the band that's not occupied. So already from this comes some sort of redundancy in the frequency domain that we can take care of. Likewise, we have isolated peaks, which means we have sparsity in time more often than not. Not always. You can see the seismic example does not look so sparse, but the ultrasonic examples look pretty sparse. So we can make use of that as well. It is the so-called slow time. So when I say slow time, I mean, I do such a measurement once, and a little bit later I do it again to see what has changed. So in this case, what we're measuring is not the time itself or the natural frequency in microsecond or megahertz, but we're measuring the rate of change of the phenomenon. How fast does it change, which resorts to slow time, as we call it, or Doppler, which would be its frequency domain equivalent to it. And again, here there is a natural redundancy in most monitoring applications because we do a continuous monitoring of something that hopefully for the most part will stay more or less stationary, evolve slowly in time due to changes, let's say in temperature or humidity, which are slow processes, or due to degradation, which is the thing we actually want to detect, but which typically, occurs after a long period of monitoring it. Meaning if we compare, measurements done at different times, there should be a large similarity, and only the difference, again, has a much lower information rate. And that is a source of redundancy we want to exploit as well. You could put the converse argument. So what would a sensor data set look like that is not redundant? Yeah. So if we're asking ourselves, okay, is there redundancy or is there not? What would a non-redundant data look like? Well, again, imagine sensor taking measurements over a fixed period of time with some sampling rates. You take some number of samples, n, then each measurement that sensor is making is one vector in the n-dimensional space. Yeah, 1 point in n-dimensional space. And a new measurement is another point in n-dimensional space. And I'm claiming these are typically quite similar. A non-redundant measurement would mean that what we would occupy would be an n-dimensional cube where all those points would be completely isotropically distributed in that cube. Yeah? It's kind of hard to imagine in 3 dimensions, but think of n equals in n, but think of n equals to 3. Think of a cube. So a non-redundant data would fill the cube entirely from all sides equally with points. But if that were all data, if a sensor would generate such data, what use would the sensor be? Because there's no structure. Why are we interested in the data? We're interested in the data because there is structure. So the actual data we care about lives in some sort of low dimensional space of the big space. Otherwise, there would be no structure to look at and we would see nothing. There would be only noise. Oh, maybe the cable's not connected. So if you have no redundancy, maybe you just didn't connect the cable and what you're seeing is thermal noise. It's kind of the argument I'm trying to make here. Yeah. So I know you've heard it all, but I like to reiterate on that because it's really an important point to remember. Redundancy is totally natural. And every useful sensor has some amount of redundancy. Can we exploit it or not is a different question. But some amount of redundancy is always there, sometimes a little, sometimes a lot, as we will see today. Okay, yeah, and then so there is a lot of data potentially. Data is redundant, so we could do data reduction, but only the fact that we can do it doesn't mean that we need to do it. Just because it's possible doesn't mean we have to. The important question is, why should we do it? What's the benefit we expect? There's at least 2 for this type of application. One is total data amount. Kind of said that earlier. If you record gigabytes, terabytes, and exabytes of data, you need to store that somewhere. Storage is expensive. Maintaining the data, finding anything in this data, it's costly and it's inefficient. The data is redundant. And the other one, and the more important one, I think, is energy consumption. In particular, when we're really talking about autonomous sensor nodes, potentially being disconnected or just loosely connected to a communication network or to the power grid, then there is energy spent in measuring and storing data, and even more energy is spent in transmitting the data. So if you can avoid transmitting some of that, you would happily do that. And that's a very good motivation for doing data reduction. We measure something, then we see, okay, before we transmit it, let's see if we can squeeze out some of the redundancy before we go ahead and transmit that. All right, so that's my brief motivation. What I want to cover today is mainly 2 or 3 things. I want to discuss a little bit about, the basic concepts. So understanding the PCA and its implications. What does it mean if it's a low-dimensional subspace? What does the singular vectors of the data have to do with that? And what's the connection to the eigenvectors of the correlation? What even is that? What's the sort of intuition also between the singular values? Why is it so interesting and so important to look at the singular values? And what's the scree plot, explained variance? And then I want to go through some practical examples. So starting with some synthetic data, looking at those ellipse plots that tell us the main directions of variance and how the PCA is good at extracting the main directions of variance. Look at that. And then I was looking for some real world data to show you. And actually I tried a lot of things that were not so nice. I even asked ChatGPT for help. And it took almost an hour of conversation and, ChatGPT suggesting all kinds of public data sets and all kinds of writing all kinds of Python scripts. None of this has really worked. So I went back to the drawing board and did it myself. I came up with the ultrasonic B-scan examples that I think are quite nice, and we can look at the reconstruction fidelity. But you can use this as a baseline for doing your own experiments. I'm happy to share all the scripts I'm showing today. So if you want to experiment further with that, you're free to do that. I have no idea how we're going to fare on time. It depends on how slow I talk. If we do have time on the end, I would have some extensions we could talk about, for instance, the kernel PCA that I think is interesting just to know what it is and what's this kernel trick. And also multilinear PCA could be interesting. That's what I did in my past life in my PhD. I work with multidimensional signals and tensors, and I did multidimensional PCA. Just in case you're interested. Again, I would have one example of an ultrasonic scan where you can see that that's a benefit. All right. So far about sort of the motivation and the introduction. And now I would want to come back to the point I was trying to make earlier. Let's see if you can maybe look at this. Right, I want to revert that. And let's see how it works here. I wanted to show you an example. So I said before, if data is non-redundant, then it occupies a cube in R dimensions completely uniformly. So all the points are uniformly spaced. And I'm trying to convince you that that is not so. And to this end, I brought an extremely simple example, a harmonic signal. I'm bringing a harmonic signal because harmonic signals are all over the place. If you do ultrasonics, if you do seismics, you have to do with harmonics because we have to do with resonant phenomena. And in fact, there is something like this, typically, of course, multiplied with a pulse function, so be concentrated in time, but underlyingly it's harmonic signals. And harmonic analysis is basically the basis for most of signal processing. So I just brought a very, very simple harmonic here, which is an amplitude times the cosine function of frequency and time. And there's, of course, also a phase. Yeah. So as for every harmonic, we have three unknowns. We have the frequency, we have the phase, and we have the amplitude. And now I want to ask the question, let's say we look at a three-dimensional example. Remember the point I was trying to make earlier, we have a sensor that takes measurements in time and in samples. These samples fill an n-dimensional space. And for representability, let's pick n equals to 3. So we sample this harmonic at 3 time points, 1, 2, and 3. And now I want to sort of visually ask the question, what is the sort of set of point, what is the space that is occupied by all types, all possible harmonics, that we could think of within these measurements that we do at these 3 time points, because that's the question we would ask. So if you want to devise sort of an efficient way of representing the data that a sensor gives you that has the task of sensing harmonics, and you don't know amplitude, phase, and frequency, you just know the time points, then you would ask yourselves, so what's the set of all possible points that these samples, these 3 samples I'm taking, could occupy? And you can vary all 3 parameters. And in fact, let's start simple. Let's take a fixed frequency, a fixed phase, and let's just vary the amplitude. So now we're looking at this harmonic signal, where now frequency, phase, and the time points are fixed and the amplitude is varied. Does someone want to make a prediction what the set of subspace will look like that these points live in for all possible values of A? Someone want to make a prediction? no wrong answers. No stupid answers, just wrong answers maybe, but that's okay. We can learn from them.
Sorry, Florian, can you repeat the question?
Yeah, again, so here's your sensor. You have a sensor that models harmonics, measures harmonics. Now I made a setup where the amplitude is varied, but everything else is fixed. The time points are fixed, the frequency is fixed, and the phase is fixed. What does the set of points look like? That we can see for all possible values of the amplitude.
A straight line.
It's a straight line, of course. Don't think too complicated. It's a straight line. So again, this is the first example of, okay, we live in a three-dimensional space, but if this were our measurement setup, then all the possible measurements we could do would be on this line. So it's hugely redundant. Right? Okay, but now you can, of course, go ahead and say, okay, well, that's a little boring, the amplitude. Let me say that the amplitude is fixed for some reason, and the frequency is fixed, but what I'm interested in is looking at the phase, because there could be some phase change. Phase change has to do with change in time, so we have a time shift, so that's typically interesting. So what if we vary the phase? Let me just look at set of points we get there. Oh, what we get is this. That looks interesting. It's this little curvy shape. But if you look at the right projection, you can see that in this three-dimensional plane, this curve, three-dimensional space, this curve actually lies on a plane. Yeah, so there is all some sort of linear dependence, but inside this plane, even more, so there's even more redundance. So it would be easy to project the 3D on a 2D because there's a plane, but inside this plane, there's also some kind of nonlinear structure. It's this kind of nonlinear relationship between the data. Huh, looks kind of neat. And just for fun, I did the third one as well. I said, okay, let's fix now amplitude and phase and just vary the frequency. And then what we get is this, that I just thought looked very neat. You can see it's this closed contour. It looks like a Lissa U figure. In fact, it is a 3D Lissa U figure. And again, it's a much smaller space than the big R3. So there is some amount of redundancy going on. But what you can see here is this is now not just some linear subspace. It's not a line or a plane. It's a more complicated figure. And in fact, the PCA is not smart enough to take advantage of this, because as we will see in just a minute, the PCA looks at linear subspaces, at planes and lines and hyperplanes in general. So a standard PCA would not be able to do that. Maybe a kernel PCA if you choose your kernel right. But still, it's a sub, not a proper subspace, but some sort of sub-volume of the big R3, meaning there is redundancy going on, meaning we should be able to take advantage of that. And we can, in fact, by doing some amount of linear compression, for instance. Yeah? But it's kind of fun because it shows you there is a closed curve, it has no intersections. So even from these three measurements, you can uniquely infer the frequency. It's no problem. Yeah? There is no redundancies. You just need to be able to do it, find a good algorithm to do it. Okay, so far about the motivation. Now let's get to business. So let me get my OneNote so we can write a few things. Right. So we're talking about the PCA today. We maybe need to distinguish it a little bit from classical data compression, because what do we do in data compression? In a sense, it is data compression, and in a sense, it's still a little bit different. Typically, in data compression, we have one incoming data set. Yeah, so there is one specific measurements that we took. Then we run it through some kind of compressor that should spit out a low dimensional representation of it, such that there is a decompressor at the other end that can blow up the data again, and we get exactly the same data set. So we can compare, or we can measure the quality of the compressor just by looking at how similar is the reconstructed data to the original data. Doing an appropriate measure for that, we can sort of see how good is the actual data compression scheme. Yeah, and the important thing is that this low dimensional data representation here needs to contain all the information so that we can reconstruct the data, of course. So there is no side channel, everything needs to be in here. Yeah, so it needs to be self-contained. But it is for sort of one specific data set. Yeah, only. And, you know, I think you all use such compressors every day. So JPEG is an example, and MP3 is an example. Your preferred video codec is an example, say MP4, and so on and so forth. These compressors are typically tailored to the specific kinds of signals. And in fact, the metric that they use to measure the quality usually has to do with what is the task we want to do with the data. So if we're compressing an image where the task is that humans should view it, then the metric is going to incorporate how do we view images and what are the things we're sensitive to and what are the things we're not sensitive to. So it's going to contain some model of the way we perceive the image, so it can leave out details that we cannot perceive. But this should not be applied if the purpose of the image is to be machine readable later on and maybe extract some sort of, I don't know, text from it. Then that would be a bad codec. Likewise, we would use a completely different technique if instead of encoding an image, we want to encode an audio file. Because then we would try to encode how do we hear music, what can we perceive and what can we not perceive. So all the psychoacoustic goes in there. Yeah. But since they are so much tailored on the specific media and on how we perceive them, they are, of course, very much optimized for these and basically, yeah, sort of unbeatable. So no matter what you do with the PCA or with compressed sensing, you will never get even close to this amount of compression. And it's not the goal. Because again, these compressors, they include a lot of non-linearities. So more often than not, these are non-linear. Because linear compression is limited in what it can achieve, but nonlinear compression is much more powerful. Yeah. So in image compression, for instance, yeah, you have a linear step. You go to some Fourier or wavelet type representation, but then you have a nonlinear step where you truncate some coefficients or you gate or you do whatever you want. And here's where the power actually sets in. So we're not going to do that for the PCA. The PCA itself is limited to linear mappings. And the other difference is that the PCA is typically not done for individual data sets, but for whole classes of data sets. Yeah. So what we do in the PCA is typically that instead of devising a scheme to efficiently represent one specific data set, we're trying to devise a scheme that represents a class of data that has a similar structure. And of course, we need to formalize what do we mean by the concept of structure. So typically it means that we have some prior knowledge of what does our data actually look like. Yeah, so we kind of know. Typically it may look like that, which if you want to be more formal means the data lives in some low dimensional subspace, and the task is to project on some subspace. So in the PCA, the task is to sort of learn the, let's say, best subspace that our data typically lives in. And there is a certain risk already associated to the typical, yeah? Because you can see that is something that we do by learning on a batch of data and by trying to grasp the overall structure of the data. Meaning it should work nicely overall, and it's going to work well if the data is nominal. But if the data is not nominal, like you have outliers, then it's not going to fit your assumption. And then you may have to look at that. In which also lies a certain strength, because what you can also do is you can apply your compression and then look at the residual of the compression. And this could point you to some anomalies. In fact, that's one of the simplest ways of doing anomaly detection. Yeah. So, and we typically do this, finding the best subspace, we typically do this by looking at the correlation, yeah? So we will have to talk about correlation in a second, a little bit more. But typically it's the correlation matrix that tells us what the structure is. Correlation is so useful because it intrinsically averages over multiple trials or multiple realizations you've seen. And the more realizations you've seen, the better will become your knowledge of the subspaces that your data lives in or your noise lives in. So again, as an example, let's say that we have, I don't know, let's say that we have something like 50 sensors, yeah, a sensor network of 50 sensors. And let's say that each of them takes 1,000 samples. Yeah. This means that overall we've constructed a 50 by 1,000 array of data. Yeah. So we could say it's a matrix, yeah, of that size. And now that means that what we actually have is we have 1,000 vectors, each 50-dimensional. So we are in a 50-dimensional space. We're looking at all our 1,000 vectors, and now we're trying to find, okay, in which subspace do the 1,000 50-dimensional vectors live? And this is what we're going to try to extract. And maybe we find a way of representing this with just a 5-dimensional subspace, yeah, just as an example. Let's say that would be possible to do. Then what we could do is we could just project the 50-dimensional data into a 5-dimensional data, and we would have a 5 by 1,000 representation of the data, let's say a new matrix, which though faithfully represents the data with some fidelity, meaning we can reconstruct the original 50 by 1,000 if we wish to do so from this without significant loss of information. But this data is much smaller because we've achieved a compression of 50 to 1, 50 to 5, meaning factor 10. So, and that is a different type of compression because it's not taking one of the axes, trying to find the best or one of the lines, let's say in X, one of the sensors, trying to find the best representation, encoding that, and then going at the next one, trying to find the best representation, encoding that. But it's looking at all the 50 over many trials and then trying to find the overall best representation to encode such data. And if new data pours in, we can apply the same sort of scheme, and it is still going to work. So, and this means it's all about projections, and the projections are linear. And of course, we have many ways of doing such projections. The PCA happens to be out of all the projections you could do. So if you want to write the math here, basically, we basically have y is equal to, let's say, phi times x, yeah? Where x is 50 by 1,000, and y is 5 by 1,000. And then phi is your projector, 5 by 50. So this is where the dimensionality reduction happens. And you will notice it looks a lot like compressed sensing, but it's not exactly the same. Because here, this phi is chosen based on prior knowledge on X that we obtained through looking at correlations. And as long as this correlation structure is true, this phi is a good one. If it were not true, it might not be a good one. But it needs to be known. So at the encoder, so at the sensor side, we need to know what the signals look like. In compressed sensing, we can choose the phi not knowing anything about X. In fact, we can use a random matrix. But here it's tailored to X, and it's tailored out of all the possible projections you could use, because there is many out there. It's the one that maximizes the variance, or I should put it right. I should say explained variance. Yeah. So basically, how much does this y explain in terms of the variance of the original data? So this is what we're trying to maximize. And only by saying that, let's maximize the variance, there's already a unique solution. You can already, just by putting this as a criterion, uniquely derive, okay, then what do these weights actually need to look like? How do you need to choose them? Okay, so that's basically sort of, yeah, a little bit the difference maybe between compressed sensing and the PCA. And as we will see also in a second, this amount of compression can in some cases even enhance the signal. And that's a little bit counterintuitive, because we would say, well, as soon as we leave something away from the data, it can only get worse. The point behind this is there is nominal sensor data and then there is noise. And if the nominal sensor data lives in a very low dimensional subspace, the noise is going to live everywhere. Then by projecting in that low dimensional subspace, we truncate away some of the noise. So we do some denoising, and that can actually be beneficial. And we will see a numerical example of exactly this happening later, where we play with the rank and we can see there is a sweet spot where the signal is denoised. And if you increase the rank even higher, it starts fitting the noise, as in overfitting. And that's what we don't actually want. So there is even an optimal choice of this rank. Yeah. Okay, right. So we're already very close to being able to jump right into the theory. One more thing is, I want to ask the question, what kind of structure are we actually exploiting? Because there's two different things. What kind of redundancy are we actually exploiting? What's actually our signals? So typically, when we talk about the signals, in terms of like what is the redundancy that they have, then there's two different things you can think of. You can think of a single sensor, and the single sensor gives you a time signal, x of t, which of course you sample into a discrete vector, x0 up to, let's say, x n minus 1. But now it's just one vector. So a PCA is only going to work if we have a matrix to work with, yeah, because we kind of need rows and columns to even be able to start defining subspaces. So how do we make this a matrix? Well, there's two different ways. Either you look at multiple sensors, and that is typically what we're going to do, or you look at a temporal correlation matrix. So you could also exploit temporal correlation in time. We're not going to look at this so much, but the PCA allows for it. So one thing you could do is correlation in time. In this case, you would come up with some correlation matrix R, which is sort of like an autocorrelation. So I'm going to write RXX here. And what I mean by this is it's basically, the autocorrelation function of x of t and x of t plus some tau. Yeah. So you can make that into a matrix, and you can look at the correlation structure of that matrix, and you can apply a PCA to it, by which you also reduce the sensor data. Yeah, but the way to apply it is maybe not as direct. You would kind of need to chunk the signal into windows, and then each window could be shrunk, and then you could reconstruct from that. Yeah, I just wanted to say that in order to avoid confusion, because depending on which paper you read, notation is going to vary a lot. And some people are going to talk about correlation in time and others about correlation in space. So I want to make clear from the beginning that's not what I actually want to talk about here. What I want to talk about is a correlation that happens when we have multiple sensors. So we have some x m of t, where m enumerates the sensors. Yeah, let's say we have m sensors, and this t, let's say tn, for n equals 1 up to n, enumerates the samples in time. So the data itself is two-dimensional, from which we can, of course, build now a spatial correlation matrix. And the spatial correlation matrix is now the expectation of x m of t, or let's say, x m1 of t times x m2 of t, something like that. Yeah. So it's an m by m matrix, which contains the correlations between the different channels. Yeah? And that's the spatial correlation that we're looking at. The advantage of this being, I need this expectation here. How do I compute the expectation? I typically don't have access to multiple realizations of the same point in time. So typically we assume that our processes are stationary in some sense and are also ergodic. And if they're stationary and ergodic, we can replace the expectation by averaging over time. And this is the way we can even get this correlation matrix to begin with. And then we can start exploiting its structure. Yeah. You could do the opposite. If you have such data and you would rather make a correlation matrix of size n by n, you could use the dimension m to do the averaging. Yeah, so everything's sort of reciprocal, and rows and columns can typically be flipped, but you have to think about whether this makes sense. This would only make sense if you have enough samples to do the average. So in this case, the number of samples we need, n, needs to be larger than m. And to get a decent estimate, ideally, it's actually much larger. In this case, if, again, you want to have some temporal correlation structure, you might want to average over space, but then the number of points in space you would have would be need to be much less, much greater than the number of samples in time. And typically that's not the case, which is why this is the more obscure setting. It happens, but it's typically more obscure. We have done work where we try to exploit the space-time correlation structure, but then what dimension do you use for averaging? So this becomes much more difficult. We used slow time in this case because it was a very slow, slowly evolving process, but that can be really tricky. Okay, That's just to make the distinction though, and I hope it doesn't confuse you too much, but I think it was important to do in the beginning because, yeah, otherwise, again, if you read some literature, you may be really confused. All right, so now that I said what we want to do, let's look at a bit more of the theory. In particular, let's look just one level deeper at this correlation that we're trying to exploit. So what does this correlation actually mean? I wrote it a little bit sloppy here, but now I want to define it a little bit, yeah, a little bit more rigorous. So in general, what we want to look at is actual correlation coefficients. And how is a correlation coefficient defined? Let's say, again, instead of M1 and M2, I'm going to use IJ just because I think that's a little bit more easy to write. The correlation between two different channels. So that's the correlation between xi of t and xj of t. So how is this correlation defined? Well, the first thing I need is I need the covariance between xi and xj of t. And I need to normalize that covariance by the square root of the variances. Variance of xi of t and the square root of the variance of xj of t. And this is typically also done exactly this way in PCA. In principle, you can do a PCA not on the normalized covariances, but on the on the actual covariances without the normalization step. But it's very uncommon. There may be some cases where there are reasons to do so, but in general, it's a little risky. And typically, 9 out of 10 papers on the PCA you read say, oh, you should do this normalization, because what you actually want to look at are correlations. This correlation is always between -1 and 1, meaning that if it's 0, the two are statistically uncorrelated. Whereas if it's 1, it means xi and xj are collinear. That means they are basically equal to each other all the time, almost all the time. And -1 would mean they're still collinear, but with a negative sign. So one is minus the other. So actually the magnitude of this correlation is what we're really interested in. Yeah. Okay, right. Now, still, this is a little bit clumsy because we have the covariances and the variances for which we still need to center our data. Let's not forget that. If I want to have the variance of xi of t, I cannot just do the expectation of xi squared of t, but I need to center. Yeah, so I need to subtract the mean, which is xi of t squared. Yeah. A very general equation that I think you've seen many times in many flavors. It's one of the fundamental equations in engineering. You see it in electrical engineering, where it reads as the total power is AC plus DC. So your AC is actually total power minus DC. In statistics, it reads as second moment is variance plus squared mean. It reads in estimation theory as MSE is variance plus bias. So there's a lot of flavors of this. It always boils down to the same thing. And as an engineer, you should develop a sharp eye for it. You should recognize it and say, oh yeah, this is the fundamental equation I keep seeing. So it's not surprising to me. I know it all the time. Yeah. So what it means for us is that it's much easier to compute this variance thing if we center the data before. And once we center the data, it's much easier to compute the covariance as well, because now the covariance, once we centered, is just the expectation of one times the other. And we can simply normalize by normalizing to the second mean. And this is typically what we do as a pre-processing step in PCA and what everybody recommends. So before you start, the first thing you do is centering and scaling. And once you centered and scale your data, things become much easier, because then this rho ij is simply the expectation of xi of t times xj of t, which is also much easier to program. Let's say a tilde for being centered. And I think it's worth looking at a simple example for this, because otherwise I keep talking in a too abstract manner. So let's make a very simple script that demonstrates that. As always, I'm going to work with NumPy here because that's the most convenient way for me of doing these things. And I'm going to work with Matplotlib to plot things. Okay, in case we need to. So, right, let's get started. Let's use, let's generate some data. So let's say we have, 2,000 samples. We have 50 channels. And now let's just generate some random Gaussian data. You can do that through NumPy with random normal, which is going to give you the 0, 1 of size n by n. Let's see if you did that right. Okay, it looks pretty okay. A is 50 by 2000. And now let's say that we wanted to estimate a correlation matrix. And let's say for some reason we didn't care much about it and we forgot the censoring. So what you can do is you can simply do A times A transpose, yeah, which does exactly that. So it gives you a matrix with all the inner products of the different channels that are in the rows, and this becomes an M by M matrix R. But now we forgot it. Yeah, we should divide by n for the good measure because we're averaging over n. If we were to look at this matrix, then what we would realize is that, well, it's not too far off because, of course, now we did our data such that it has variance 1. So in fact, it works quite well. But let's say that the data of the variance of our data was not 1. Let's say the variance of our data was, let's say 100. Yeah. Then if you did that, you can see that on the main diagonal of this matrix, you can still see the variance of the data, and you actually don't want that. So it's not a correlation this way. So it depends a lot on the scaling. And why is this actually bad? This is particularly bad in case you have channels that are differently scaled. So you may have one channel that's 10 times stronger or 100 times stronger than the other one. Then it's going to totally dominate this matrix and you won't even see the rest. This is why this normalization makes a lot of sense. And in fact, it's relatively easy to do, especially in Python. All you need to do is subtract the mean. You can actually do it like that. So Python will realize that there is a matrix, there is a scalar, so I'm just going to subtract the scalar from all the elements. And once I did that, I can simply divide by the square root of the variance, which we know as a standard deviation. And this is easy to compute in Python through the std function. Yeah, so I can say, okay, I want to compute the standard deviation of A, and I want to do it along the axis with the number 1. So axis with the number 0 is the rows, axis with number 1 is the column. So please do it along the columns. If we do that, we get a vector of length 50 that contains all the standard deviations. Yeah. And now I want to divide A by all these standard deviations. So I might be tempted to say, well, let me do it like that. This is not going to work. Why? We have a matrix of size 50 by 2000, and we have a vector of length 50. So you can't divide it directly like that. But there is a simple fix for that. Because if instead we extended this to be a matrix of size 50 by 1, then Python would realize, oh, there is a thing 50 by 2000 and 50 by 1. I'm going to do what Python calls broadcasting. MATLAB calls this binary singleton expansion. It's exactly the same thing. So it's going to apply the same operation on all these elements, just, one by one. Yeah. Or yeah, right. And we do that through reshape. Exactly. Someone has said it in the chat. Or that's one way of doing it. So how do I reshape? Just like this, right? 50 by 2000 would be one way to do it. Yeah. So let's see. Oh no, this doesn't work. No, of course not. Like that, 50 by 1. Yeah, it's a length 50 vector that we reshaped into a 50 by 1 matrix. By the way, there is a fun trick that you can do. If you don't want to hard code the 50 here because it looks like a magic number, okay, I could write M, but then I need to remember that if I change anything else about the line, the M is actually tied to the size of A. there's a fun trick. You can write -1 here. -1 means Python, please figure it out yourself. Yeah, Damian, you wrote it in the chat. That's great. You're right. Exactly. You can write -1 and then you have it like that. That's one way of doing it. If you've seen this before, you know what it is. If you haven't seen before it, readability is a little bit, yeah, so. Just to show you one other way of doing it, you can also tell Python to please just include another axis. So you can say, okay, give me all the elements along the rows, and after this, please just put a new axis. It's debatable whether that's more readable than the other one, but these two versions exist. And now you can say we have a nice correlation matrix where the main diagonal is equal to 1 and everything is fine. Yeah. Okay, that's just on the centering and scaling. I just wanted to show you real quick how you can do this. Of course, there's also packages that you can use for that. You don't have to do it yourself. But sometimes I find the readability of these steps a little bit better if you know what you're doing and if you're doing it by hand. Okay, now we have this, and now we need to actually work with this matrix and estimate the subspaces. Yeah. And for this, I was planning a very short recap of the basics of linear algebra. But yeah, I think I'm trying to keep it short because I don't want to bore you too much with this. Right. So let's look just into linear algebra a little bit more, just to remember. Again, what's our setting here? We have a vector, let's say x of t. I'm writing this as a vector, just stacking in the different sensors along the rows. Yeah. And the idea was, again, this lives in a, let's say, m-dimensional space. But due to structure, we believe that this occupies just some subspace of Rm. Yeah, it lives in a linear, in a linear subspace. If it actually lives in a linear subspace, this means that we should be able to describe it linearly, meaning there should be a basis A such that x of t is a of t times something else, let's say s of t, where this A is now, let's say, m by p. Yeah? This s is p by 1. And if that is satisfied, it means that now x lives perfectly in a p-dimensional subspace of Rm, which is described by the columns of A, provided that the columns of A are linearly independent, of course. Yeah. Okay. Right. And in such cases, the matrix A dictates the whole structure that is underlying to this to the subspaces that are in there. Because again, looking at the columns of A, A1 up to AP, they are supposed to span a p-dimensional space. And the whole goal of the PCA would be to get a decent estimate of them. Yeah. So what it means is that in the whole Rm, which is the big space, there must be some p-dimensional subspace where the data lives. And any vector outside this linear subspace is not plausibly explained by our model, so it can't be part of the data. Yeah. So really think of this, let's say, three-dimensional space, m equals to 3. Some sort of two-dimensional plane laying here. Let's say it's this plane, just for simplicity. Yeah. Then this is spanned by two vectors, by A1 and A2. And in this case, our data would live in this plane, as described by x is a times s, and any point outside the plane would not be part of our data. So then the compression that we actually want to do to represent this data efficiently is simple. Just project the data into this plane, into this lower dimensional plane, and then this basically already compresses the data. So. And again, if we had noise, which we often have in engineering, so if our true model is like this, A times S as before, but then plus noise, then this noise term is going to live everywhere. It's going to live also outside the plane, meaning if we project the data into the plane, then we actually kill some component of the noise that is not compatible with our low dimensional nature of the data. Of course, not all the noise, because a part is still inside the plane, but the part that's outside the plane. And this is some amount of denoising that can actually help to improve our data fidelity. Yeah. Right. And now the only question is, how do we actually project data in this low dimensional space? And the answer to that is we can use the singular value decomposition or the eigen decomposition. But I actually want to talk about the singular value decomposition because I think it's the most helpful for us. To this end, I'm going to take the x again. I'm going to put it into a matrix as before. So we have x of t1 up to x of tn, like this. It's an m by n dimensional matrix. And I'm going to write this is equal to A, which is m by p multiplied with, and for s, we can do the same, s of t1 up to s of tn. And again, that is p by n. So why am I doing this? Because now I have a matrix, and now I can apply a singular value decomposition to this matrix. And the singular value decomposition is going to give me projectors for all the subspaces. So what does it look like? Let's say this is now our matrix X, and we compute a singular value decomposition. A singular value decomposition decomposes X into 3 matrices. One of them is the matrix U, the matrix of left singular vectors. One is the matrix sigma, the matrix of singular values. And then there is a matrix V, and we need a transpose here, which is the matrix of right singular vectors. Now, this matrix here is unitary. It means that all the columns are mutually orthogonal and they're all scaled such that they have norm 1. The matrix V is unitary as well. And the matrix sigma is diagonal. And on its main diagonal, and on its main diagonal, it contains singular values, which are real valued and ordered by magnitude. So we have sigma 1 up to sigma r, if r is the rank, and the rest is 0. Okay, this is basically the singular value decomposition. And one more ingredient, then we can look at an example. The matrix U here, I haven't written the sizes. U is m by m. This matrix here is m by n, and V is n by n. This matrix U can be partitioned into 2 submatrices. So I can say, let me consider the first R columns, m by R. This I'm going to call US. And let me consider the remaining columns, UN. And this will be m by m minus R. Yeah. Why S and N? We typically call them signal subspace because this is where our signal lives in. And noise subspace, as I just said before, noise is then the only thing that does not live in the subspace where our signal is. That's why we can call it noise subspace. Though be careful, this is the subspace where only noise lives, but not all noise lives in the subspace. Some of them also lives in the signal subspace, unfortunately. Otherwise, life would be much more simple. Still our matrix sigma here. And for V, we can do the same. We can partition it into VS and VN. But we won't be using V much here. We will mainly be using U, N by R, N by N minus R. And now the amazing thing, the first time I saw it, I could almost not believe it, and it's been amazing me to this date, is that the 4 matrices that I just wrote, they give you awful normal bases for all the subspaces that are relevant with respect to the matrix X. So I didn't delve into the linear algebra too much, but I already said that the set of columns of A spans a subspace. We call it the column space, or the range of the matrix, or as I just said, the signal subspace. And a basis for this is found here. So this gives a basis for the signal subspace. which is in fact the one we're looking at. Single subspace. UN gives you a basis for the left null space. VS gives you a basis for the row space. In case you want to work with the rows instead of the columns, you can always do that. And VN gives you a basis for the kernel of the matrix or the null space. Okay, but we care about the signal subspace, and that is exactly the projector that we will need to carry out a PCA. So we're almost here, we're almost there. Now all the ingredients come together, because the fun thing is that once you have a basis for a subspace, so this is an R-dimensional subspace of Rm, and US is a basis for it, we can immediately find a projection matrix P just by taking US times US transpose. This is how you project a vector into a subspace once you have a basis for it. Yeah? And we will use exactly this to project our data, and that is basically the essence of what the PCA does. The PCA does this step, the US transpose step, at the encoder, let's say, where you compress the data. And this step here, the US, is the decoder if you want to reconstruct the data. Then that's exactly what you do. But let's look at one example to make that a little bit more visual. And after this example, I guess I have to make a break. So, but I still would want to do this just for sort of visualizing the fundamental concepts a little bit better. It's a very simple example, but I thought it might be helpful for you also to see it and actually believe it. So let's say that we have such a basis. I called it A before, yeah. So let me make an example, yeah. Just doing 1, 1, 0, 2, 0, 2, and 0, 0. So that would be my matrix. Let's see if I got what I wanted. Print A, yes. So you can see it's a matrix with 2 columns. So it spans a 2-dimensional subspace of R3. And now let's say we do an SVD of it. So we do something like this, USVH, you can actually write it like this. And you find the SVD in the linalg subpackage of NumPy of A. And now you get 3 matrices. And now let's have a look at U. And you can see this is now a 3 by 3 matrix, which contains 2 subparts. The first part is an orthonormal basis for the space spanned by the first 2 columns. And the third one is an orthonormal basis also for the complementary space, or the space not spanned by it. It's probably instructive to plot these vectors a little bit. So again, let me do some matplotlib magic. And let me in fact do the matplotlib widget thingy so I can manipulate the plots a little bit better. All right, here we go. Let's do a figure, and let's add a subplot to it where I want to see the, oh, come on. I want to see the 3D projection a bit more nicely. All right, fair enough. And now I want to be able to draw a vector. So I just make a shortcut because it's easier like that. I simply say to draw a vector, you start from the origin, you go to the first coordinate. I don't know if there's a built-in function to do that. If you know one, let me know. I usually just write it myself because it's easier. Kind of like that. Yeah, so this way I can plot a vector. And this way I can now have a look at the first column of A. Let's see if that works the way I want to. I need to do show. There we go. And the second column of A. There we go. So you can see that what I did is I defined a basis for the XY plane, but the basis is not orthonormal. Yeah, so you can see that these vectors are pointing, are not orthogonal to each other, but they form a basis. And now we can compare that to the orthonormal basis that we got through the SVD, because what the SVD gave us was also two vectors. And the first one is U0. So let me draw that in blue. And the other one is, is U1. And now you can see that these two vectors, they span the same subspace, but now they are orthogonal. Yeah, so you can see they're perpendicular to each other. So this is just, to prove that this very simple way of doing things actually gives me an orthonormal basis. And in fact, I can draw U3 just for good measure. And you will see that, now it's a vector pointing upright. So it's perpendicular on the plane. So it's a basis for the orthogonal complement of the vector. And the other thing I want to show you is, let's say now we get a new incoming vector. Let's say something like that. I need to do an NumPy array, otherwise it's not going to work. Then what I was claiming is that we can get a projector on, let's say, the signal subspace just by taking U 0, 2, 0, 2, U 0, 2 transpose, kind of like that. And then, let's see if that did what it should. Yeah, ignore the 10 minus 17, that's just a rounding error. You can see it's 1, 0, 0, 0, 1, 0, 0, 0, 0. So it's actually a projector on the plane, which we can see by saying AS is a PS times A. Oh no, I cannot do that. AS is PS times A. Yeah. And likewise, we can get a projector PN from this other column, from U2. How do I actually do this? 2 like this. 2 like this. And that's a projector for the other one, AN, like this, which, if we did our math right, should be so that AS plus AN gives back A. And we should, sorry, I did the times. I should have done the matrix multiplication here, because times is the element, y is multiplication, like this. So you can see AS plus AN is our original vector, and these are now the two components of the vector, which we can see just by drawing them. So let's draw vector AS in green, AS in green, and AN in green. So, and now you can see hopefully what happened. Yeah. So our original vector, I haven't drawn that one yet. So let's add it as well. A. Our original vector A is this long green one here. So it was pointing out from the plane. And what happened to the projector is it got projected down on the plane, which is this vector, and decomposed sort of like in the part that's in the plane and the part that's sticking out from the plane. And this decomposition is that simple. It's just the two projectors here, PS and PN multiplied, which you get from the columns of the SVD. Yeah. So it's really as simple as that. I don't know if you find this example too oversimplified or helpful. To me, like when I saw this for the first time, I was immediately, no, I need to try this. I don't believe it. I don't believe how a matrix as complicated as this U from the SVD, which contains all kinds of weird fractions, is going to give me something so simple like this projector. But it does. And in fact, it's actually how this works. And yeah, this can be used to run the SVD, but I think to run the PCA. And we can continue after the break exactly with an example of the PCA, which is what I would want to do next. Unless there's questions now, feel free to shoot them. Otherwise, we have a break for how long do we do the break? 10 minutes, 15?
I think we said 15.
15 minutes? Okay, then, yeah. thanks everyone for now, and see you again in 15 minutes.
Thanks.
All right, then let's continue. If there's no questions up to this point, now we have actually all the ingredients together and we can finally put together the whole PCA, because let's see what we have. So we learned that if we have the data X or the corresponding covariance R, which you can compute as X transpose. So, I mean, sample covariance, I should be a little bit more correct here. Divide by N if you want to make it correct. If you have either of them, you can estimate a basis for the subspace that contains most of the signal energy, so the dominant signal subspace, just by applying the SVD. If you apply the SVD to U, what you get is you get the matrix US, which contains a basis for the signal subspace that you want. Likewise, by the way, you can take the eigenvectors of R if you prefer that. Again, take the eigenvectors corresponding to the largest eigenvalues. They give you exactly the same US. Up to some scaling ambiguities, it should be exactly the same. Then we can project the data on the lower dimensional space. So our X projected, let's say, would be US times US transpose times X. Why is this helpful and why is this a compression? We see that immediately when we look at this matrix. Let me call that Y. This matrix is now of size. We said what is the size of US? Yeah, we said it's R. So this matrix is now of size R by N, whereas the size of X was M by N. So you can see that Y is smaller than X if R is smaller than M. So if there is a low rank subspace at play here, which means that we achieve a compression of factor M over R. In the previous example, M was 50, R was 5, so the compression was 10. Yeah. And that is basically the idea. So what we will do at the encoder, at the transmitter, is to do this projection, Y is transpose times X. We have this matrix U, which is now our compressed, let's say, representation of the data. This we transmit. And if at the decoder, we want to recover the original data, all we need to do is US times Y, and we get this XP, which is the data projected on the low dimensional subspace. Yeah. So of course, this means that the matrix US the basis for this low-dimensional subspace. It has to be known at the transmitter, at the encoder, and at the decoder. And this is maybe the slight distinction that we need to make also a little bit between the PCA and standard compressed sensing. So just very quickly here, for PCA, we compute US dependent on the data. So dependent on X, at least some training data sample, and US is known. Yeah, okay, well, I mean, it's known to the transmitter and to the receiver, but to devise X, we kind of need to have access to the data. Whereas in compressed sensing, the matrix phi with which we compress can be chosen independently of X. And I mean, of course, again, it has to be known at the decoder as well, but the encoder does not have to know anything about the structure. Yeah. So that's maybe the difference. Okay, but anyways, so that's basically how a PCA works. Get the dominant eigen vectors of the covariance matrix or the dominant singular vectors of your data, applies US transpose times X, here's your SVD, and at the decoder do US times this to get the data back. One more comment before we look at the example is, what's the amount of error we make, we might ask. So the error we make is between this XP, this projected data, and our original data. How big is this error? Let's say we want to know what's the squared Frobenius norm, just the sum of the squared errors. Well, that's relatively easy to compute because XP is nothing but US times US transpose times X minus X. And now you can do the math here, and it's just a few lines of proof. You basically insert the SVD of X and you play around with all the corresponding quantities. It's relatively simple to do. I will spare the few steps in the interest of time and just tell you that the result of this is that the error is exactly equal to the sum of the singular values squared, sigma n squared, counting from r plus 1 until as many as we have, let's say m. And that is a very interesting relation because it tells us that just by looking at the singular values, we can have an idea how much we can compress, and we can choose the rank. And once we chose the rank, we also know what is the amount of error we will make. So we will look at the singular value profiles just in a second, but I already told you that singular values are always real valued, ordered by magnitude. So there's a strong one, and then maybe a little bit weaker one, and so on. And if we have data that has a low dimensional structure, you will typically see a few of them sticking out, and then there will be a few more, which represent maybe our noise. And now we know from this formula exactly what happens. If we choose the rank equals to 3, we cut here, then this is the amount of energy we retain in the signal, and everything right of it is the amount of error we make, which could be part of the signal we're truncating because it's not interesting. It could also be noise by truncating. But this is sort of a really elementary and important thing to understand about the PCA, in that it is very important to look at the singular value profile before you start, because this will allow you to judge, is there even any low rank structure in there? And if so, what is the rank that I should maybe consider? So either you look at the singular values like that, or maybe better, the squared singular values. You can also look at the cumulative sum of them, which is going to approach a maximum value, 1, if you normalize. Then you can kind of judge, okay, how many percent of the original data, if you do the square root, am I having? Am I looking at 95% of the variance, or 98 or 99? And then you can define your own cutoff as you want. But let's take an example. Let's look at this in terms of the example we already started here, where we just drew some random data. So what we can do now that we have the data is we can compute the SVD. Like we just did in the linear algebra example of A. So this gives us bases. Don't need this plot anymore. This gives us bases. And now we can basically, we can do this, or just to compare, We could also do the eigen decomposition instead. So we can do Eich here. And the eigen decomposition returns 2. It unfortunately, in the other order, it returns the eigenvalues first and then the eigenvectors. And we're going to see that these are similar, but less dimension. Oh, sorry, not A, of course, but R. And we should be able to see that these are similar. So if you look at the singular values, those are in S. You can see here the singular values. And they should be related to the eigenvalues, L. Now these do not agree because there is some scaling in between. So we divided by n here. So if we want to undo this, we would need to divide this by the square root of n. But then it's still not the same because what did I do? No, I didn't want to do this. These are still not the same because the singular values are not exactly the same as the eigenvalues, but the squared singular values are. So we need to actually square this, and then we can get rid of the square root, and then it should be the same. Okay, so what we can see here, and let me just plot them real quick. S, let's do S squared over n, why not? S squared over n, and I think I need to do some x-axis here, otherwise it's going to complain. Okay, there we go. Here we can now see the singular values, the decaying singular values. Now you can see the low rank structure we were looking for is not there for this type of data set, but that's not surprising. It's not there because this is just white noise. So white noise is not compressible. So we would not expect any strong decay. You can see your slight decay, but that's always there. The slight decay just comes from the fact that the random singular values get ordered by magnitude. And since there's some amount of variation, there will always be one biggest and one smallest. But there's no clear cut here. And you can see the decay is so slow that the error of truncating just 1 or 2 would be probably too high to tolerate. So compressing white noise this way makes no sense. But again, that's not surprising. Exactly what we expected. Anyways, that's basically the PCA. And now if you were to choose a rank, you could basically say, okay, now my compressed data is just, I take U, let's say first, I don't know, R columns, for some R, let's say 10, transpose times X. And then, sorry, not times. I keep writing that. Matrix multiplication is the add operator. I didn't call it X, I called it A. There we go. And now we've reduced the size. Yeah, so now Y has size 10 by 2000 compared to the original data, which was 50 by 2000. So in this case, it would be a compression of factor 5. But for this data, the error we would make would still be very high. Well, I mean, mathematically speaking, of course, it works. And the reconstructed would just be take again U, 0R, and multiply it with the compressed data that you received. Then you have the reconstructed, which now again should have size 50 by 2000. So we can see that here. Yeah. So that's one way that you can do the PCA. I wanted to show you a second way because, of course, you don't actually have to program these things by hand. There is some very good packages for that. And in fact, the one that's probably most frequently recommended to use for this is the scikit-learn package. The scikit-learn has a lot of decompositions, including the PCA. So you can just import a PCA like that. And then it is as simple as saying, decompositions, why does that not work? Decomposition, not decompositions. Okay, there we go. And then PCA is as simple as invoking the PCA, telling him how many components you want. Components equal to, let's say, R. Or depending on how you want, you can actually compute the PCA with all the components in case you want to choose your rank later. Or you can say, I already know my rank. I only want the first 10, only compute them, then I'm fine. But then if you want to have one more, you need to redo it. So depending on what you like. You do one way or the other, and then you do PCA fit A, and you're done. Yeah, and then you get this PCA object. And this PCA object has lots of useful things. For instance, it has the, what is it called? Explained variance. So that's exactly the thing I was showing earlier. So this tells you how much of the variance of the data is explained if I truncate to rank 1, rank 2, and so on and so forth. So it's basically a plot very similar to that above here. Yeah, they call it a scree plot. Right. And if you want to have access to the component, well, first of all, yeah, this is your fit. If you want to now actually transform data, so compress data, you have data incoming, then you can do PCA transform, and then you basically put A in and you get Y out. So here I passed the same variable, but this would not have to be the case. So you could fit the PCA based on some training data, and then of course apply it to new data, and then you would have your compressed data. Yeah. So it's basically, it has functions like that. In fact, even the scaling can be done in scikit-learn. If you found this mean and STD not so nice, then you can, there is pre-processing schemes here, pre-processing, and it has a standard scaler. And the way this works is very similar. You invoke the standard scaler, has no arguments, and then you say A scaled, for instance, is a scalar fit transform A. So it will standard scalar standard. Oh, I need to run this and then run this. Yeah, so that's one way you can do it. The advantage being this code is more readable. I'm not so much a fan of external dependencies, I have to say. I don't like to make myself dependent on packages because it can always happen that support ends for the packages, then you're screwed, or the interface changes even. So in general, I advise you to be careful and use external dependencies only when you really need them. In this case, you might say, well, PCA is simple enough, I don't need them. But scikit-learn is really a package that's been out there for many, many years, and it keeps being maintained and extended. I don't think it will die anytime soon. And the advantage of this code is, of course, that it's very readable. So we know exactly what happens here. It's a standard scalar. It's applied. Okay. We know what happens here. PCA is fitted and data is transformed. So that's an advantage of the readable code. Okay.
If I might say, the disadvantage of using such libraries, for instance, in my case, it's like if you just import PCA and you have no idea what is actually underneath. Yeah, the moment it doesn't work, which happens often, then you have a hard time to understand what you're doing wrong because you don't know actually the technique you're trying to apply.
Right.
So that's a bit my situation because I've done it in the past, and sometimes worked, sometimes didn't. But
I appreciate your comment very much. Thank you. Which was one purpose of this lecture, to show you how these few lines of PCA are also just a few lines of actual SVD code where you exactly know what happens, and you find all the things that you do in the SVD also in the PCA package, so you could even compare the two. Yeah. So if you look for the U, by the way, it's also in there. It's called components. So if you look at PCA components, this is basically the U matrix. So that's the transfer matrix that does the low rank, low rank projection. Okay, time's already quite advanced. I want to show you some real examples. But to speed up things, I'm going to stop doing live programming now and just use the examples that I prepared. The first one I prepared is a synthetic B-scan. In fact, this was taken from a GPR example that I did, but it applies just like that also to ultrasound. The idea is relatively simple. I generate a synthetic B-scan for an ultrasonic measurement just by assuming some pulse shape. So I just take a modulated Gaussian pulse, that I define as a pulse function. Then I sample that according to some sampling frequency and some number of samples in time, and I create a corresponding time axis. I sample it in space using some sort of spatial separation. So you can see here it's actually an ultrasound example. And then I define myself time of flight between the points I measure, the scatterer where the signal gets scattered, and the signal going back. I define locations of scatterers in X and Z and amplitudes. And once I have this, I can generate a B-scan from it. So simple enough. It's, of course, a very simplistic model. Yeah, it's no real ultrasonic wave propagation, but it's just based on timings. That's what the B-scan looks like. And now we could run a PCA on that. So we just do an SVD, and we just look at the scree plot. And that's what the scree plot looks like. So you can see I had 50 spatial measurements here, and you can see how there is some low rank nature going on. So this is a cumulative plot of the squared singular values. And you can see, yeah, rank 1 is not enough. But if I go to, let's say, rank, what is it here, 10, 11, 12, 13, it seems I'm explaining a lot of the variance. So this might actually work reasonably well. Here is an example of a rank 3 approximation. So what I do is, again, the same thing. I'm just computing the rank 3 approximation of my data. And then I'm plotting it. And you can see here the B-scan, it doesn't look like exactly the same. Also one column of it, which is an A scan, original and reconstructed. And you can see, okay, there's some error. So rank 3 was not enough. But as we go higher in the rank, let's say using rank 5 or so, it already looks better. There's still some error. And then as I go to, I don't know, rank, let's say 10 or so, then it starts becoming quite faithful. I do have an interactive GUI for that. Oh yeah, one more thing. Another type of plot that I recommend to do, I call them rate distortion plots. And it's very similar actually to the scree plot. So what you do is you vary the rank that you consider, the PCA rank. And each PCA rank corresponds to a different compression, which you can plot on this axis. So 1.0 would be there's no compression. And the lower this number is, the more compression there is. So this is the rate in terms of ratio of retained samples, if you want. And on the vertical axis, you just plot the distortion, which is basically the mean square error in reconstructing the original versus the compressed data. And I have 2 lines here. And the one line, sorry, the legend is missing. The one line is the actual B-scan where I show, okay, as I increase the rank, the distortion goes down. And of course, the number of retained coefficients goes up. So I have different points in this trade-off curve between amount of compression and data fidelity. That's great. But I have another line here, which is the blue. And the blue is doing the same just with white noise. So the reason I'm incorporating this is as a benchmark, because you can see even with white noise, depending on how you choose your axis, you may have the feeling that some compression is going on, because eventually, the amount of distortion does go down as you increase the rank, but the compression is not exactly great. So it is important to have that as a benchmark to know, okay, how much better are we compared to white noise? And you can see we're doing hugely better here. So there is, some strong reason to believe that there is actually a lot of low rank structure going on, and it makes sense. And then I have this interactive plot where you can actually play with this rank. So what you can see here is the original B-scan that I chose, the reconstructed B-scan for a certain rank, the difference between the two, that's the error. And here we can see the scree plot with a red line indicating where are we currently in the scree plot. And what you can do is you can vary this rank here, and you can see how the plots update. So if you go to the extreme case, to the rank 1, you can see how it's not able to reconstruct this hyperbolic shape. It makes some sort of rectangular shape because rank 1 is like outer product between a column and a row. So every column is collinear. So the columns, they kind of all look similar, just scaled by a different number, which is why everything looks so parallel. So this is not possible to do with a rank 1. Oop, now I did something I didn't want to do. How do I zoom out? Shit, sorry. Accidentally, I zoomed the plot. Let me just recreate it. Okay. So yeah, that's the rank 1. Therefore, the error is of course quite big. Then as we go to rank to higher ranks. Let's say rank 2, yeah, still not exactly great. Rank 3, it starts curving. Rank 4, rank 5 is where it starts resembling at least the parabolas. And then as we go higher, you can see how the difference goes down, becomes smaller and smaller. And in fact, here at rank 8, we have a compression factor of 5, and we have a mean square of 0.004. We already have a very accurate reconstruction. Of course, you can go even higher. Yeah, you can go to rank 9, 10, 11, 12 if you want. The mean square error becomes practically 0. The compression becomes, of course, lower and lower. Now we're just at factor 3 compression, and as you go higher, it goes to 1, which means no compression. Yeah. Okay, so that's a synthetic data set. And you can do the same here with the A scans. You can also see how faithful they're reconstructed. Rank 1, it's not exactly great, especially the asymmetry of the pulse only gets, yeah, really mapped once we go higher in rank. I did the same thing with a measured B scan, and I want to show you that as well. So that should be this plot here. Let's see. Is it this? No, I think I need to rerun the cell. So that's actual measured data that we measured ourselves in the lab. This is one of our specimen, one of our steel specimen, which has some flat bottom holes, and you can see small hyperbolas here indicating the flat bottom holes. In one depth, there's more flat bottom holes here in different depths. This is the back wall echo. And again, you can do basically the same game. So you can start with rank 1, and you see how for rank 1, it focuses only on the back wall because it's a rank 1 structure. Yeah, it's constant over space basically, and you can do that nicely. You can see the shadowing here, the acoustic shadowing of the flat bottom holes. It reproduces that, but the actual hyperbolas are not visible. And then as we go higher in the rank, you can see how it starts reproducing these flat bottom holes, and it becomes more and more faithful. And you can see here the compression of about 10. The mean square error is 0.01, so it's a very accurate reconstruction. Yeah, it works quite well. Right. I did the same also with a publicly available data set by BAM. I can share the link to it later, but I downloaded it just last week. There is this data set that has been published by Ernst and his collaborators. And again, you can basically play the game, same game with it. You just exchange the data. And that is what this looks like. The data contains a lot of stuff. I just picked the first file I could find. I don't know if it's the most representative, but I mean, the gist of it is that also for this data, it works reasonably well, and we can do some amount of compression. You have to be, of course, a little bit careful in this difference plot, because especially in ultrasound, sometimes it's small details that actually matter. So saying, oh, there is the small thing of 0.1 or 0.01, I can ignore it. It's not always true. Sometimes it's the small things we look for. But the good thing is that eventually, as you kick up the PCA rank, everything gets explained. Eventually, even the small things are in there, and you can drive the mean square error down to 0 if you go high enough. Okay, that basically is the examples with real data I wanted to show. I would have one more on 3-dimensional data if you wanted. But of course, if you want to ask questions instead, that's also fine. It's not something I have to cover. It's just extra material that I have, if you like.
Could you share the source code?
Of course, yes. I'm happy to share the notebooks I made. They're sometimes a little bit chaotic. Not sure how much time I'll have to clean them up, but yeah, I think for the most part, they should be understandable. So yeah, happy to share those.
Florian, we share them within the doctoral candidate, but not on the web, or do you want?
I would say we share them among this crowd. If someone from external is interested, they can always contact me, and I can arrange that.
Okay, so maybe we can add something, Fatima, on the website saying contact USES2 if you want the Jupyter notebook. And the video will be the video will be posted. Do you agree, Florian?
Sure. Yes.
Yeah, so we can add, if you want to have access to the Jupyter notebook, either contact maybe directly yourself, Florian.
Yeah.
Okay, contact Florian. Okay.
Yeah.
Florian, I have a question, if I may.
Sure.
I was wondering if with autocorrelations, so the other way, let's say the process somewhat is the same or there are major differences, because
yeah,
sometimes I focus on only one sensor,
right.
and I want to see if the autocorrelation makes sense or not. But
I would say it's the same. If you just have a one channel, what you need to do is you kind of need to break it into windows. At least that's how I would do it. Maybe not the only way of do it. Of a certain size, T. Of course, they can be overlapping, but let's just draw it like that for simplicity. Like that. Then you arrange those as columns or rows of a matrix. Yeah, like this and like this. And yeah, I think you get the idea. So you get a matrix that's basically sort of like a reshape. So if they're not overlapping, it's just a reshape of the original samples. If they are, then there are some repetitions and some copies. And then you take this as a data matrix, X, and then you can run it through your PCA framework. What would happen is it would now look for correlations inside this length T windows to exploit, which again would mean that if these length T windows have something like, I don't know, 100 samples, but the correlation structure makes it so that they live on a low dimensional space. Let's say there is some, I don't know, harmonic oscillations in there or some other low dimensional feature. Then you could compress each of those windows to fewer components. And then these fewer components would give you also some amount of compression. Or again, you could also, of course, go the other way and say, okay, this model is my nominal measurement. I subtract that, and everything I have left is then the anomalies maybe I'm looking for. So I would say it's the same process you can use. There's not much difference other than that. Yeah.
okay, thank you.
All right, other questions?
So maybe I've got one. Maybe you said it during the lecture. Maybe can we use this for filtering out some, you take the third value, third or fourth component, and in it there is a wave that is very small, but that is interesting, as you said.
Yeah. So yes, of course, this could in theory be done, and of course, there's various ways of doing so, and the PCA is one. So sometimes people use the PCA hoping that certain features of the signal will manifest themselves in certain components. So this is now really about separating components, as in component analysis, and then PCA is of course one, a principal component analysis, because the basic problem behind it is to say, if we have a linear mixture, X is A times Y, we cannot uniquely, just by looking at X, we cannot uniquely separate the components. Why? Because there's infinitely many ways of doing that. So we need to impose some additional constraint if we want to separate the components. And the PCA does that by saying, my constraints is that the components are orthogonal. So if I can live with that, if I say it's physically meaningful and plausible to say that I have different components that are orthogonal to each other in an algebraic sense, which translates to statistical uncorrelatedness in some sense, then PCA may be a method of choice. And you may be lucky that the component shows up in one PCA component or in a few that you can filter out. More often than not, it's not. And people are not so happy with this uncorrelatedness. And then they resort to other things like, for instance, ICA. Yeah, where instead of the principal component analysis, it's the independent component analysis. And there the assumption is that the components are statistically independent. So if this is a better assumption, then the ICA may work better. And I think for filtering components, this is usually preferred because statistical independence can easily be argued. If the source, the physical source of this of the signal you're looking at is a different one, then there is actually no reason why they should be statistically correlated. So more often than not, they are independent, and then it's easier to, you know, hope that they show up in different components. But there's many other blind source separation techniques that do this. And in fact, if we bump to 3 dimensions, we can look at CPD or Tucker decompositions. Then there's even more ways of doing this.
So I'm not sure. I've heard about ECA recently, I would say, and it works only if it's a linear problem. No, there is an issue.
Well, everything I said today is about linear. The PCA also only works if it's linear. Yeah.
Okay.
In a sense, yes. I mean, if you have nonlinearities, there's other things you can do. And there is an extension of the PCA, the kernel PCA, which we did not talk about today, which can deal with nonlinear structures. But in general, yeah, linearity is assumed. And if you have nonlinearities, you have to see what you do about it. But linearity is really tantamount to this, because typically we work with superpositions of sources. And these linear superpositions only make sense if you have linearity. If there is some nonlinear thing going on, they anyways mix, and it's much, much harder to tell them apart.
Okay. Well, I don't know if you have other questions or comments.